Alright, on the last day of these basic differentiation rules, what we're really going to stress is the rate of change. There's two types of rate of change we're going to read, average rate of change and instantaneous rate of change. So let's look at this picture to see if that can help us out. So average velocity or average rate of change is the slope of the secant line. So it occurs over an interval, maybe from 2 to 5. Well, it's average velocity or average rate of change. Those are both the same words. Can be described using the slope of this line. However, if I talk about the velocity at a certain time, that's talking about the tangent line to the graph. Or if I say instantaneous rate of change, that's talking about the tangent line to the graph. So let's go ahead and just look at this problem and see if we can answer a few of these questions. I want you guys to notice the notation that S of t we're going to use for our distance functions. We're going to use v of t for velocity, and we're even going to get into acceleration sooner or later, so I'll go ahead and say that a of t is our acceleration. We're not going to use that today. This one says find the distance traveled after 2 seconds. That's just simply saying to find s of 2. So the distance would be 2 squared plus 2 plus 1. So the distance would be 4 plus 2 plus 1, which is 7. Or we can put a label in that 7 feet for this because it says s of t is in feet. Find the distance traveled after 5 seconds. So that's asking me to find s of 5. So that would be 5 squared plus 5 plus 1. That's 25 plus 5, which is 30 plus 1, which is 31. Then it asks you to find the average velocity from 2 to 5. Average velocity is, remember, the slope of the secant line. So we're really just looking at finding the slope between 2 points. So the 2 points that I have for this would be 2, remember the distance at 2 is 7, 2, 7. And the distance at time 5 is 31, and 5, 31. So you can describe the average velocity to be, I don't know why I wrote it that way. Average velocity equals the change in distance, or the change in s over the change in time, which is the same thing as saying s of 5 minus s of 2, that's your change in distance, over your change in time, 5 minus 2. The time was 2 to 5. So we found s of 5 to be 31. We found s of 2 to be 7, all over 5 minus 2. That ends up giving me 24 over 3, which is 8. And we described that as feet per second. It's the same thing I would have done if I had just used the slope formula from Algebra 1. 31 minus 7 over 5 minus 2. The next question says find the instantaneous velocity. Well, in order to do that, we would just be taking the derivative of s of t. So the derivative, so I'll go ahead and write that. That would be the derivative. So the way you get to your velocity is by finding the derivative of your position function or your distance function. It would be 2t plus 1. So the velocity at 2 would be 2 times 2 plus 1. So the velocity at 2 is equal to 5 feet per second. And the second one here, the velocity of 5 is equal to 2 times 5 plus 1. So the velocity at 5 is equal to 11 feet per second. Notice the average of those is 8. You add them together, divide by 2, you get 8. It's another way of coming up with the average velocities by finding both instantaneous velocities. So to reiterate what I just talked about, I talked about how the average velocity is the change of s over the change in t, change in position over the change in time. Instantaneous velocity is the derivative of that position function or that distance function. And this will become useful later when we have to write our own position functions, and we'll actually do a little bit of this today. Any position function can be written as s of t equals 1/2 the gravitational pull, that's what this g is, the gravitational pull. I'll just put gravity there. t squared plus, this is the initial velocity, and then s of 0 is the initial position. And I'll come back to this slide in the second video as well to explain these a little bit more. On my next problem, it gives me this position function that I ran through in the last slide, or the last video, where this is the initial velocity, this is your initial position, and this is the gravitational pull. The gravitational pull is 1/2 g. And this one, it's feet per second, and the gravitational pull for feet per second is negative 32 feet per second squared. So what they did is they took negative 32 times 1/2, and they get, that's where this negative 16 comes from. All right, so let's just go ahead and fill in things that we know. By reading this, it says a ball is thrown straight down from the top of a 220-foot building. So that would be the s of sub 0, that's your initial position, with an initial velocity of negative 22. That's your initial velocity, or that's your v sub 0. What is its velocity after 3 seconds? Well, let's first write the position function based on that information. So my velocity was negative 22, and my position is 220. So now I'll be able to figure out the velocity, because velocity is the derivative of your position function. So the velocity is equal to negative 32t plus negative 22. The velocity at 3 seconds would be negative 32 times 3 plus negative 22. So I end up getting negative 96 plus negative 22, and so the velocity would be negative 118 feet per second. The next part of this says, what is its velocity after falling 108 feet? So here's this building. It's 220 feet tall. The ball is now fallen 108 feet. So it's gone down 108 feet. Well, this position isn't 108 feet. It's 220 minus 108. It still would have another 112 feet to fall. 112 feet. I wrote 122 and I said 112. So it says, what is its velocity after falling that many feet? Well, we need to know what time that occurs at. So in order to figure that out, I'm going to have to say, well, where or what time is the position 112? So I'm putting in 112 for my position, or into my position function, and then I'm going to solve for t. I'm going to set this equal to 0. Move the 112 to the other side, and that gives me a positive 108. Now this is factorable. I will factor this by taking out a negative 2. That gives me 8t squared plus 11t minus 54. I'm going to take the guesswork out of the factoring and do it for you. We have 27 and negative 2. This gives me a negative 16 and a positive 27, so it does factor. And so the time, this time isn't going to apply because you get negative 27 over 8, so you can't have negative time. This is the one that applies when t is 2. So the last part is, since you're supposed to figure out the velocity of that, we need to find out what v of 2 is. V of 2 would then be negative 32 times 2 minus 22. So we end up getting negative 64 minus 22, and so our velocity would be negative 86 feet per second at this position when there's, after falling 108 feet. All right, for this problem it says, so look at the graph and draw its velocity function. Now, the first thing I want you guys to realize is that we have distance over here, so we're talking about a distance function, and they want us to find the velocity. Velocity is the derivative of distance, so it's asking you to find the slope of the tangent lines to the curve. Well, this has a constant velocity here. It has a constant slope, a constant tangent line to the curve. Every tangent line that you draw to this curve is the same. So really what I'm going to do is I'm going to just find the slope between these points. Now I'm going to tell you that this is 6, 5, and this is 0, 0. So we're going to go ahead and find this slope, and we do that going 5 minus 0, y minus y, over x minus x, and I get 5 over 6. Now let's put some labels with this so it makes more sense. This would be 5 miles in 6 minutes. And so it's y's over x's. So 5 miles every 6 minutes would be what's going on from 0 to 6. Now, we don't really travel in miles per minute, so let's change this to miles per hour. Well, in order to change this to be 1 hour, I would be multiplying this times 10, because that would give me 60 minutes, which is 1 hour. So I'll multiply this by 10, and I'll get 50 miles per hour. Now that's something that we can relate to a little bit better than 5 miles every 6 minutes. Then what's happening from 6 to 8, that's pretty simple to see. That the derivative, or the slope of that line, the slope of the tangent lines, is 0. So this is from, let's go ahead and do this, from 0 to 6, and then from 6 to 8, we're going 0 miles per hour. And then from 8 to 10, let's see, this point right here is 8, 5, and this point right here is 10, 6. So we're going to find the slope of it. So we go y minus y, 6 minus 5, over 10 minus 8. So this gives me 1 mile every 2 minutes. Well, that would mean, to change this to be 1 hour, I would be multiplying this times 30, because that would give me to 60 minutes. So times this by 30, and I'll get 30 miles per hour. So now I can go ahead and draw the velocity function based upon this information. So I've still got time down here. Let's see if I can make this a little straighter. So my time, I'm still going to put 2, 4, 6, 8, 10 down here. I'll label it time. And we went ahead and changed this. And you know, we have this in miles per hour. So I actually should change the bottom of this to be in hours. So let's go ahead and do that. No, I don't need to do that. I apologize. I changed my mind. So 2, 4, 6, 8, 10 minutes. We can use the velocity over here in miles per hour. We can still keep this time in minutes, and that's fine. What I want to put over here is I just made the velocity. You could have also done the velocity in miles per minute. I just changed it to miles per hour because that's something we're more familiar with. And so then I'll just go ahead and place this as 10, 20, 30, 40, and 50 miles per hour. Now remember, things are not differentiable at endpoints and corners. So I've got things that are not differentiable, so I'm going to have some holes on my graph. So when I create this, from 0 to 6 minutes, okay, from 0 to 6 minutes, I'm traveling 50 miles per hour, and it's a constant rate, so 50 miles per hour from 0 to 6 minutes. From 6 to 8 minutes, I'm traveling 0 miles per hour, so it's just lying down here. I'll scribble that in darker so you can see that I put something there. And then from 8 to 10, we're traveling 30 miles per hour. So from 8 to 10, I'm traveling 30 miles per hour, constant rate. Now remember what I said, you can't find the derivatives at corners, endpoints. That's why we have holes here, because those values do not exist on the velocity graph.